Okay, we're going to start. Today I was told that we're going to have a brighter picture or sharper picture because we have a new gadget in the broadcast system. I don't know whether that's true or not. Hello Tokyo, can you see it very clearly?
Yes.
Oh, okay. How about the Hiroshima? I understand Hiroshima may not be online today. Oh, okay. Anyway, I'm sorry that we had a technical problem as well as administrative problem because on Wednesday, so we delayed our class to today. This will be our last class for our friends and colleagues in Japan. Anyway, last time we talked about the Wigner-Weil distribution. You see, the Wigner-Weil distribution actually is no different from Fourier. Instead of t minus tau, the Wigner-Weil divides t minus half tau and t plus half tau. So it's the central correlation rather than one-sided correlation. But what's different is here is that instead of just make a transformation with respect to tau and get a function of omega, Wigner-Weil also recorded the time t over there. So at each time t, you plot a Fourier spectrum. Okay, so at each time t, you plot one Fourier spectrum. You move another place, you plot another spectrum. So as a function of time frequency, you have a sequence of spectrum depends upon how close you want this t to be. Then once you have this spectrum, then you can plot it, the contour, and that's Wigner-Weil. Wigner-Weil actually is identical to Fourier spectrum. So this is how Fourier spectrum was defined in its original form. Yeah. Now, how to define frequency? Because at each time you have actually a full spectrum. Then in that case, you will not be able to define instantaneous frequency. So Wigner-Weil defines instantaneous frequency by this moment method. This is Wigner-Weil as function of t. It multiplies t, get the first moment and divide it by the zeroth moment. Okay, so that's how they define instantaneous frequency. So this instantaneous frequency is not any frequency. It's the average of frequency. So if you have two signals, it will give you one value. Is that reasonable? I don't think so. My objection is to assign one frequency at any given time. Okay, that's the basic, I think, illogically unreasonable definition. For example, we go to a symphony and we have different instruments playing at the same time. Of course, a different instrument will not play at the same frequency. You may have the bass drum, you may have the violin or whatever. Okay, when you recorded the symphony music piece, what you got? You actually get a time series. And if you use this, then at any particular time is only one frequency. But what you hear are actually many different sounds. You can hear violin, you can hear drum, you can hear all kinds of instruments. Depends upon how sharp your ear is and depends upon how your training is. So at any given time, you don't just have one frequency. And if you arbitrarily, well, not arbitrarily, if you forcefully define one frequency, that frequency has absolutely no physical meaning. Yeah. Our data, in fact, is not just one signal. Our data, actually, in the complicated data, it's like a symphony. Yeah, except it's not music. So it should have all kinds of frequency at the same time. So therefore, forcefully define one frequency and define frequency this way, I don't think it's reasonable. Yeah. So Wigner-Weil will give this kind of definition, and if you compare that to short-time Fourier, Short-time Fourier may have a window, but but it's the same thing. Yeah, and because of that, so Wig and Weil claimed one thing is that their marginal spectrum is identical to Fourier spectrum. Yeah, because plus t minus t, it's the same. Plus and minus 1/2 tau, it's the same. And therefore, they have the so-called marginal requirement. But there's another interesting property pointed out by Leon Cohen to justify, in a way, to justify Wig and Weil distribution. What they say that if I have X, and X consists of two signals, then if I do a Fourier transformation as S omega equal S1 omega S2 omega, so this is additive. In other words, Fourier transformation is linear. It's additive. However, you have to think that the power spectrum density is not linear. Power spectrum density is not getting from X, it's getting from correlation function of X. The correlation function of X is actually S squared. If it's S squared equal to S1 plus S2 squared, then S1 squared plus S2 squared plus 2 times the multiplication. Therefore, S squared does not equal to S1, S2. And that is what Leon Cohen came up with. A very strange argument. This is because the Fourier spectrum, if we have two signals, they will have some crosstalk. Therefore, Wig and Weil should also have crosstalk. And the reason that they brought this up is that Wig and Weil people claim that if you have two independent events, this event cannot be separate. For example, not only that, the Wig and Weil people also claim another thing, as I said, the marginal requirement. The marginal requirement is that Wig and Weil, once you expand in the time frequency, if you added everything together, it will be a Fourier spectrum, of course. So they put the marginal requirement as the marginal to be the Fourier spectrum. So let's check. How about wavelet? Will wavelet give you marginal power spectrum if the wavelet is sine function? If the wavelet is actually has very wide window, then the orthogonal base should satisfy this requirement. The continuous wavelet is not orthogonal, so it has a loss redundancy. Wig and Weil distribution has the marginal distribution identical to power spectrum density. Yeah, this is what they really want people to believe. This is our time frequency spectrum is good because we can sum up to power spectrum. Yeah. So a genuinely instantaneous frequency will not satisfy this requirement. Yeah. In other words, if we use instantaneous frequency, we may not add up to power spectrum density. But the energy, however, is conserved. We have the same energy, but different distribution. Yeah. Spectrogram does not satisfy. The spectrum has different windows. If you use window too small, obviously you will not get lower frequency components. So that will not add up to the power spectrum density. But all of this requirement, I don't think it's reasonable because this is not a reasonable requirement. If PSD is inadequate to begin with, why should I sum up to power spectrum density? The power spectrum density cannot resolve time, cannot resolve all kinds of things. So adding up to power spectral density is not a virtue, it's not an advantage to me. So I don't think it should be used as a standard. Now let's look at the case of whether we can separate two events. Now here I have actually two waves. One wave like this, the other wave like this. That's two waves at the two different locations. one here, and then move to closer, eventually merge. So it propagates from 7, 6, 5 forward eventually to 1. So clearly, I have two waves. This two-wave packet is totally independent to each other. Okay. If we use Fourier analysis, can we clearly separate these two? No, because the Fourier is from beginning to end. In order to satisfy this and satisfy that, locally we have to introduce many other components. So if you plot the Fourier spectrum, the Fourier spectrum have very broad spectrum, but very different magnitudes. Yeah. The reason you have that is to fit different kind of combination of the two. So Fourier spectrum clearly is influenced by the presence of both waves. Now, if we use Hilbert spectrum, however, we clearly identify one wave packet here, the other wave packet there. And these are two independent packets. I should be able to separate. Why not? Yeah, we did separate it. And if you use wavelet, a wavelet is also separate. However, the wavelet, because the different wavelet to fit that particular wave package, it may not fit very well, so it is spread vertically through this. This is continuous wavelet, by the way. So both wavelet and the Hilbert spectrum can separate two independent packages of wave without any problem. But Fourier cannot. And because Fourier cannot, in other words, if my two waves stand here, I have one spectrum. Two waves stand here, I have another spectrum, because the Fourier component will be different, right? So, and if we use Wiegand-Weil, what we will get? Wiegand-Weil, if you give one wave, it's here. You give another wave, it's here. If you treat waves separate. If you put both together, it will identify one, identify the two, but also have a shadow in between. In other words, if you have both waves there, I can do a spectrum here. Of course, I get mostly the influence, the input here. If I have a time exactly over the other frequency, I get that. But I also get the interaction term. But if you get here, you get both waves, so you also get interaction term. So this is why Wiegand-Weil has this problem. This is called the cross term. So Leon Cohen and the people dedicated to Wiegand-Weil has come up all kinds of windows, all kinds of weighting functions, and eventually some of the windows, some of the weighting function can get rid of this, but not totally get rid of everything. Yeah, and that is I think it's definitely a shortcoming of Wiegand-Weil. And if you put the spectrum, if you measure the spectrum, you find component 1 is here, component 2 is here, component 1 plus 2, it's not exactly separable. And here is how we compare. This is Wiegand-Weil, and over here, if you look carefully, you can see some contours. The contour is the wavelet, and this bar line is actually Hilbert. Yeah. So if we have two events, two independent events, and if you really want to separate it, Wiegand-Weil is definitely another method. And wavelet can do it, and Hilbert can do it even better because it clearly defines the frequency. Actually, in this case, the package is a Gaussian modulated sine wave. Yeah. So, and if you look at the marginal spectrum, you see the Fourier spectrum spread very widely. And the reason it's spread wide is because it has to add other components just to make the signal more local. And the Hilbert spectrum, however, is extremely sharp. in that particular location. Yeah, you can look at the Hilbert spectrum comparison with Fourier. And if we look at the length of day data, use length of day data as an example, you will find that the Fourier spectrogram, it has this clear time step over there. This one time step, another time step. And as you go up, the time step is almost continuous, means this is pretty constant, and this is also constant. This is actually monthly, this is half monthly. Then we have all kinds of harmonics over there. Yeah, indicating that the tide, the moon tide, or the solar tide, it's not actually one component. Based on Fourier, this is not one component. This actually has a lot of modulation, and the modulation gives you all kinds of harmonics component. If you use, if you blow it up, this is actually the way to see it up to. This is half month. This is monthly. This is half monthly. Now, if you use Wiggin and Weil, you see what's the difference? The difference is that you still get this half monthly. You get the monthly. You get all kinds of harmonics. Then, in addition, you get a lot of interesting patterns. Okay, those interesting patterns are really not anything new. It's just crosstalk. Yeah. How you get this? This is you get that data. You plot the spectrum. You cut this through. It's a spectrum using that point as a center point. You go to another place, you get another central point. Get another spectrum. So spectrum after spectrum after spectrum, glue it together, and you plot the contour. This is the Wiggin and Weil. The Wiggin and Weil, in fact, it's not much different from the from the Fourier spectrum, except that it has a lot of this cross-talking term. Yeah. And the same data, if we use wavelet, then we also get half monthly, we get monthly, we get the spectrum. You can see that the component is not a single line in wavelet. It's already its harmonics and or the sidebands are show up over here. We have monthly, we have half monthly. The half monthly is the strongest. Now, Hilbert spectrum is totally different. Hilbert spectrum, this half monthly is fluctuating up and down. That means the half monthly is a nonlinear signal, and so is the monthly is also nonlinear signal. And this at the beginning of the time, near the 1960s, we have a lot of average. We averaged all the nonlinearity out. Yeah, it's not because the Earth or the Moon is behave any differently. Yeah, so these are the difference. Then you can see that using different method, you actually will get different presentation. This is a different presentation, however, we have to be very, very careful to interpret. Yeah. So this time frequency analysis, the wavelet, spectrogram, and HHT can all separate simultaneous events with different degree of fidelity, but Wiggin and Weil cannot. Wiggin and Weil have very strong crosstalk. Yeah. Now you have to use a lot of the. They have defined different windows and different weighting function, try to suppress that. But I don't think it's totally successful. The instantaneous frequency defined by moments in Wiggin and Weil is crude and illogical. I don't think that's right. Yeah, like the example I give you in case of the symphony. Yeah, we clearly can hear different frequencies, but why should we use only one? No. Just because we recorded this one-time series, but that one-time series has different frequency added it all together. And to separate it out is the goal of our analysis. So even though Wigner-Weil satisfies the marginal energy requirement, it does not give Wigner-Weil any advantage of time frequency analysis. Satisfied marginal requirement is not a advantage, it's not a virtue. Yeah. It's just because your marginal is power spectrum density, but we have already said power spectrum density is a problem. So to equal to that, I don't think it's any claim to of success or proof of success. Okay, so here this is the time frequency analysis, and we're going to move to another topic. Okay, you have already. Thank you very much, Mr. Su. This will be the last class for our friends from Japan, so I will use this as a summary of our discussion. This is the paradox on instantaneous frequency. Yeah. Many people think that we should not have instantaneous frequency. Yeah. People like at the beginning, we talk about, people say that the instantaneous frequency, the word should be added out of the dictionary. The reason is that most people think of frequency, they immediately think of 1 over t, 1 over period. Yeah. If you do not have a wave, how can you define frequency? And if you only have part of the wave, of course you cannot define frequency. So the instantaneous frequency is very controversial. And for those people that use Fourier analysis exclusively, they also think instantaneous frequency is impossible. Because if you use Fourier analysis or any integral transformation, there are uncertainty principles. Yeah. You can either define time very precise or frequency very precise. You cannot define time and frequency both very precise. So then in that case, how can you define instantaneous frequency? You pick up a time, so this is my instance. Then your frequency spread that wide. So what is the instantaneous frequency? You don't know. So if you pick a frequency very precise, so this frequency happened at what time? It spread time-wide, just like we just saw in the in the spectrogram. So the time becomes spread out. So either way, you cannot pin down a particular point in time frequency space to say that this is my instantaneous value. Okay. So the objection for the instantaneous frequency is very, very strong for a while. Okay. And particularly by Leon Cohen. Leon Cohen in 1995, at precisely the time I developed Hilbert analysis, he published a book called The Time Frequency Analysis. I told you before, Leon Cohen almost dominates Wigner-Weil transformation. Now, everyone use Wigner-Weil transformation always refer to Leon Cohen. And because Leon Cohen used this title, and he, for very unreasonable reason, that he dominates even this name. Wavelet analysis will never say they are time frequency analysis. Yeah, in fact they are. Actually, they are many aspects they are better than Wigner-Weil. Yeah, but then Wigner-Weil dominates this. So in his chapter 2, which is the title is Instantaneous Frequency, and they list a bunch of paradoxes to challenge the fact that there is instantaneous frequency, especially instantaneous frequency through Hilbert transformation or any other methods. Let's look at what is his objection. And today, after we discuss the Hilbert spectral analysis, we should be able to answer all these objections or paradox. Paradox number 1, instantaneous frequency of a signal may not be one of the frequency in the spectrum. See, that's, well, by the way, I have to say, by spectrum, you mean Fourier spectrum. Okay? So, instantaneous frequency of a signal may not be one of the frequencies in the spectrum. So, if I have, say, spectrum lines, and that's what he means. I have two signals. I put in two signals, I have two lines. Okay. But the instantaneous frequency may not be the two of the lines. May not be one of the frequency of the line. For a signal, this actually is the same as that, very similar. For a signal with a line spectrum consists of only a few sharp frequencies, the instantaneous frequency may be continuous and range over infinite number of values. He thought that was unreasonable too. If we have just clearly see lines, and then the instantaneous frequency is continuous. Continuous, of course, can have value in between the lines. And that is also the same thing here. See, may not be one of the frequency in the spectrum. See, I have spectrum in lines, and you have frequency other than the lines. Yeah. So these two are actually the same. Number 3, although the spectrum of an analytical signal is 0 for negative frequency, the instantaneous frequency may be negative. Yeah. You know, when we do Hilbert transformation, how did we do Hilbert transformation? We use Gabor's program. Gabor's program is that you have a signal. By the way, these are discussed in the mathematical part I give you for reading. Okay, if you read it, you will find it. So the Gabor program is that if I have a signal x, I do a Fourier transformation. I have both positive and negative frequency. I cut and throw away the negative frequency and do an inverse transformation. That inverse transformation turns out the real part is your signal, the imaginary part is the Hilbert transformation. So the Fourier transformation is from minus infinity to infinity of x e I omega t. Okay? Then once I get the transformation, I have omega from minus infinity to infinity. If I inverse transform, but I do not do minus infinity to infinity, I do 0 to infinity. Forget about the negative part. Okay, then I would get the real part plus Hilbert transformation. So what he says here is that the spectrum of analytical signal is that the signal that I have Fourier transformed, I cut the negative frequency and threw it away and inverse transform. And so that is the analytical signal. And that signal in Fourier spectrum does not have negative frequency anymore, right? Because my negative signal is set identical to 0. Then why the instantaneous frequency may be negative? He cannot understand that. Yeah. So then for a band limited signal, instantaneous frequency may be outside the band. So this one and this one, 1, 2, and 4 are actually identical or very similar. You have bandwidth, but the instantaneous frequency can be outside the band. You have a single line, the instantaneous frequency can be continuous. And you have certain frequency, the instantaneous frequency is not there. See, it's not one of the frequency. That's if my band has a limit and the frequency is not in the band, it's not one of the frequencies. So these are genuinely identical things. But I think when you write book, you may want to make the book a little bit thicker. Perhaps so you repeat this, but it's identical. So this 1, 2, 4 are similar. 3 is a different issue. And the last one, the value of instantaneous frequency should depend only on the present time. True. If I calculate the instantaneous frequency, I should calculate with the information right at this moment. Yeah. But the analytical signal from which the instantaneous frequency is computed depends on the signal from minus infinity to infinity. Yeah. Because Hilbert transformation is integrated over everything, then the analytical signal, if analytical signal is determined from signal from everywhere, then the derivative, even though you use derivative cannot be local. In other words, the derivative is influenced by other places. So that is true. Yeah. So we have all this. Now if we use Hilbert spectrum, sooner or later you will run into people that harbor this kind of doubts. So in this rest of this class, I will try to explain why this is not true. Yeah, how can we defend ourselves against this kind of question? Observation number 1, I combine. See, by spectrum, Cohen is limited the term to Fourier spectrum. By instantaneous frequency, Cohen is limited the term to IF obtained from Hilbert transformation. That's their limit. Okay? So in fact, as we see, IF could be defined from many other methods. We have already discussed that. Yeah, we'll see. Paradox 1, 2, 4 are essentially the same. Instantaneous frequency may be different from the frequency in the spectrum. Negative frequency from Gabor's construction is an issue. And Hilbert transformation is not local, is another issue. In fact, all of that can boil down to these 3 objections. So resolution of paradox 1, 2, and 4. 2 examples. We have gone through this example many, many times. Yeah. If we have 2 sine waves, then plot together, we have a beat. Yeah. And once you get this beat, and this is already IMF. So we do the frequency, we find that the frequency actually is pretty constant except at this joint point. At the joint point, the amplitude is very, very small, and the frequency can momentarily be very high. You may ask, is it, well, a beat should be just a beat. How come you have locally high frequency? Yeah, and if we calculate from Fourier, yeah, short-time Fourier, what do we got? We got a very broad frequency band, and we also get this higher frequency value. So that higher frequency value, if you look at locally only frequency of that time, of that particular instant, you do have this problem. And that is spectrogram. And you compare this, is just one line between almost at 5. You see how wide this is. Yeah. And the colorful background is actually wavelet. So you compare wavelet with Hilbert spectrum, you also see that momentarily you may have something different in that particular junction when the amplitude is very, very small. So all method, if you look at the local period, local duration, you will have some anomalies. Yeah. And in a way, this also answered the paradox number 5. That is Hilbert really local even though you integrate very far? Yeah, it's pretty local. Yeah. And if you compare the normalized Hilbert, which come up here, with generalized zero crossing, In other words, if we give up everything, this is I just count zero cross of all the wave, you also will get constant frequency and suddenly jump, constant frequency suddenly jump. These are the nodal points. In fact, if you use generalized zero crossing, it actually jump up even more. Yeah. So that is if you block up everything, if you really look at the local and the local area indeed has such anomalies. And you can look at it. You can look at this even. By the way, there's a typo. This is generalized zero crossing. This is Hilbert. Not this way. It's the other way around. Okay, make sure to correct it. This is zero crossing. Yeah, zero crossing has steps, and generalized normalized Hilbert does not have steps. Yeah, we should change. I should change that. And another thing is that if you look at the marginal spectrum, what you then find is that the Hilbert spectrum gives you just one component, and the Fourier spectrum actually gives you two. This is something which everyone first encounter Hilbert transformation or Hilbert analysis will ask, how come I put in two frequencies? You're going to give me one frequency out. Yeah. So this is indeed the case. And there are other spread like that very large frequency, and that large frequency does not actually add up probabilistically. So the highest, the most likely value is the beat, is the average frequency. So you can change this. You can change the beat, and you still will have this thing at the nodal point. Most probable frequency is still here, not here, and you have again two peak versus one peak, and this can go on. The reason is why we have only one, because we have sine A plus sine B equal to sine A plus B and cosine A minus B. So either you have two separate frequency, or you have one frequency with high frequency and low frequency B. They are mathematically identical. I can give you either way. They are equivalent. They are equally good. There's no superiority to say that I give you two frequencies, therefore I have to get two frequencies out. Yeah, we'll come back to that even more. Now, this is some new development. In in a paper published by Railings and Patrick Flandrin, he actually specifically asked the question, one or two frequency, the empirical mode decomposition answer. This is published in the IEEE. This paper saved me a lot of problem. From 2008 and on, anybody say, oh, I put in two frequencies, I will get only one. I just send this paper to them to read this. Okay. What this paper say is that close tones are no longer perceived as such by human ear, but are rather considered as a whole. One can wonder whether a decomposition into tone is a good answer if the aim is to get a representation of what you perceive, or you want to get a mathematical answer. Okay. So what they say is that if I put two sine waves together, I put it together, it actually becomes a beat. And if you put that beat into a computer and let the computer generate the sound, you listen to the sound, and the sound actually is one frequency, but frequency amplitude start to modulate. You don't hear two sounds. Okay, so from physical point of view, our ear only listen to instantaneous value. Our ear does not stay for 5 minutes and integrate to aha, there are two sounds. Our ear never will do that. Like when I speak, immediately you hear what I speak. You don't wait until 5 seconds to integrate what I speak in and analyze into spectrum. That's not possible. So human perception is locked in instantaneous value. Yeah. If you have two waves, if the two waves are close enough, then you are not going to hear two waves. You're going to hear only one. The only thing I did not do, or they did not do, and I think it should be done by some of the physiologists, is to play two tones and find out when they can actually see two, can hear two, rather than hear only one. And I think that's a very worthy exercise. So, so they raised this question: so should we match physics and or perception rather than to match mathematics? That's precisely the kind of question I have asked for the last 10 years. And I think that we should look for physics rather than mathematics. Why I should look for physics? Because mathematics is some structure, some framework that we define. Why we should see two? Because we have sine function, sine cosine function. And sine cosine function, through certain mathematical operation, we can separate the two. But if I hear something, this something is AM, the amplitude modulated. Why should I say that there's only two, there consists of two frequencies? We cannot hear that, and if I give you any local region, you will never be able to tell that. Yeah, you can only tell that if I give you infinite long. See, those frequency, these two frequency is separable, depends upon how long the data is. If the data is short, these two will be together, because the resolution of the Fourier spectrum depends upon the total wavelength, total data length. If the total data length is short, these two will merge together. Yeah. So the other way to see is that we can have two frequencies gradually separate, and we take a shorter and shorter time span to try to hear this sound. Yeah. Then we'll find out how long our ear actually are integrating. I think our ears are very sharp because the ear can hear very short duration sound or high pitch sound. And in order to hear that high frequency sound, then our integration must be very, very small. Anyway, so this is a question that he asked. And you can see that if I put in three frequencies in there to give you the very complicated signal, we can actually separate it out into the signal. We can get 1, 2, 3. We can get 3 components. Yeah. So it's separable in some case. Then he studied another thing empirically. What he did is that I have a cosine F1 plus A2 cosine F2 with arbitrary phase shift. This is his signal, two frequencies. He wants to find out when I can sort it out. But because it's two frequencies, we have 6 parameters: A1, F1, Phi1, A2, Phi2. So he rearranged this signal into a simpler. The simpler is that I have a cosine 2 pi t. That's frequency 1. Yeah, 1 radian. Well, plus cosine 2 ft plus phi. So we only have 3 variables: A, F, phi. A is the amplitude. This A amplitude is, in a way, is the ratio of the two. So this is the low frequency, is the high. This is the high frequency, low frequency. So he normalized the high frequency to be 1, and take the second frequency to be a lower frequency. So this F is between 0 and 1. So this is a lower frequency amplitude signal, and the amplitude is A2 over A1. So it's the amplitude is, see how high is the second frequency, the lower frequency. Yeah, and phi equals to phi2 minus phi1. So we'll study this, and the derivative is that. Then you see that if the low frequency amplitude is low, the low frequency amplitude. The combination of amplitude and frequency is low. What you see is that the low frequency, if it's low, it always cuts the high frequency at the given points. But if low frequency is very, very high, then you also cut the low frequency at pretty regular pattern. The problem is here. It's not very high, but it's also not very low. Then the low frequency, the high frequency cut at the different. See, over here you can go the whole wave without even cutting, even crossing the high. But over here you cut at 3 places. So in this case, if you try to use EMD, you will not be able to sort it out. In this case, it's very easy for you to extract it. So with this, then he defined a measure, a criteria. This criteria is D, which D is the first IMF. If you put this data in, what it will be the first IMF you get out? Remember, first IMF is always the high frequency, right? So the high frequency minus cosine 2 pi t, which is the high frequency component, divided by the low frequency magnitude. Yeah, because Hilbert transformation always bring out the high frequency first. So the first is always high frequency. Compare the first high frequency with the high frequency signal. If this is 0, that means I'm successfully bring out the high frequency, right? If it's 1, that means I totally missed the high frequency, because the high frequency compared to the high frequency, it's nothing. This then becomes the low frequency component. So he did a numerical experiment. Yeah, this is the frequency, the lower frequency. On this end, the low frequency becomes very low, very long. Okay, at 1/2 means the low frequency is half of the higher frequency. Yeah, at 1 means low frequency equal to high frequency. Okay, here is the amplitude. Yeah, at this range means low frequency components is very, very strong, very high, equivalent to this case. On this end means low frequency is not very strong, and that equivalent to this case. So the high frequency peak are all clearly visible. Yeah. So what you see is that if the low frequency amplitude is low and the frequency separation is high, we can always separate the 2 components. But if the frequency becomes so close, and close up to say near 0.6 or 0.7 or 0.8, by the time it's 0.8, there's absolutely no way that they can separate out. Yeah. So this and if the frequency separation is very high, and even if the amplitude, low frequency amplitude is very large, you still have a chance to separate the higher and low frequency. Yeah, this curve is Patrick Flandrin has a lot of time and a lot of computer time. He always do this kind of numerical computation. Like when he studied white noise, we study only one kind of white noise. He studied all kinds of noise, different color noise. Yeah. So this answers the domain. This domain answer is only mathematically. That means in this plan, the Hilbert transformation could separate, the EMD could separate 2 components. Now the question, Linton, the question is whether physiologically we can separate. I think that would be a very, very good research topic for you. Maybe if you want to do that, this is a very fertile ground. Yeah. And we want to see if physiologically we can also separate this. Yeah. I do not think our ear actually works as a Fourier analyzer. Yeah. And this will be the test. Could be a test. And this is the three-dimensional graph, and this part is the criteria C. Yeah. If it's equal to 1, forget it. Okay. If it's equal to 0, you can separate. In between, that's the hard part. Yeah, that we don't know. And this is a different plot of the previous curve. So 1 or 2 frequency. That's the question. See, mathematically, if you select strictly Fourier base, it is 2 frequency signal. And if your signal is long enough, we always can separate the 2 signals. Physically, it's a modulated 1 frequency signal. And that is also mathematically equivalent to the 2 signal by virtue of the trigonometry identity. Yeah. So using EMD, we can separate the signal if the amplitude frequency combination satisfies certain condition. The condition coincides with physical perception. This is the part we need to prove. Yeah. The fact that he plotted that does not imply physiologically indeed is the case. And what is the condition? The condition is if frequency separation is more than a factor of 2 or the amplitude of low frequency is relatively small, then we can separate. So this is the condition. So in the future, if anybody asks you, say, I put in 2 frequency, only give me 1. Yeah, go read this paper. Okay? Or you can tell them that it's physical versus mathematical. Yeah. In fact, mathematically they are equivalent because of the trigonometry identity. Example 2, the Duffing pendula. We have gone through this many times, and Duffing pendula gives you sharp crest and sharp trough. And this is omega plus, this is actually, you expand this out equal to omega, 3 omega, and so on. So Hilbert spectrum only gives you frequency around here. Fourier spectrum gives you frequency all over the place. And this is Fourier spectrum. And this is what Leon Cohen's puzzle or paradox. And I'm surprised that he will actually bring this up. Here are spikes, Fourier spectrum. And here are the instantaneous frequency. Yeah, he says instantaneous frequency. I have a spectrum, it's not here. Yeah, and I have a frequency here, it's not in the Fourier spectrum. So this is a paradox. What is the difficulty? I cannot see that. Yeah, the difficulty is that if you recognize this as a frequency, this as a frequency, then of course these are outside your bound. But listen, what is your phase function? What is the most theoretical, precise definition of frequency? The most precise and most mathematical definition is time derivative of phase. And in this particular case, we have the phase function. What's your problem? We just take the derivative of the phase function, we get this. Yeah, and if you cannot get that, it's your problem, not our problem, right? So this is something. It's when I read his paradox, I don't know what to do. When I saw him, I told him, and he still scratches his head. I don't think he has think outside the box. If you lock in yourself in the Fourier, you will not see the other dimension. In other words, if you leave a two-dimensional world, when somebody's outside the plane, you won't see them. Yeah. So this is one of their paradox. And now, once you know this, you'll find this paradox is very laughable. Yeah. It's not anything very profound or very difficult to answer. It's very relatively easy to answer. And if you do Duffing, continuous Duffing case, and we will have a continuous spectrum. And this continuous spectrum is very different from the from the Fourier-based or wavelet or whatever. Okay, and in this case, we have a lot of harmonics straight line. Here, the frequency is only, this is already approaching to chaos. So our frequency is still only over here, except that here we do have even in Hilbert spectrum, we actually pull out the forcing function. This is the system response, and this is actually the subharmonics. Yeah, we do have some noise over here, but if we do a cleaner job, I think we can suppress this noise to much lower frequency. Yeah. Now another one is Rossler's equation. Rossler equation is the one that had amazed the nonlinear community to no end. What it is that simple nonlinear equation system, it eventually generated this kind of oscillation. You see, this kind of oscillations looks very benign, yeah. But when this fall in the hand of nonlinear dynamics community, it created big shock. The shock is that here, if you decrease the nonlinearity, this wave is very regular. It's just one wave after another. All amplitude and everything is the same, except the frequency is more or less look like the water wave. It's a sharp crest and a round-off trough. Okay, but when you tune up, increasing the nonlinearity more, and what you have is one wave becomes bigger, the next wave becomes smaller. Not only that, they are so regular. Then you come over here, you come to here, this wave is identical to that wave, this is identical to this. So what you have is that this is a periodical oscillation. Originally, period is one wave. Now period becomes two waves. See, from here to here, it will repeat exactly. From here to here, it will not repeat exactly. Yeah. So this, when the nonlinear dynamics community get hold of this, what is their method? Their method is to plot the time delay. And time delay is to look for periodicity. And originally there's only one period, it's one wave. Now they have to suddenly switch to two periods. So they give them a very fancy name. It's called the period doubling, bifurcation. Yeah, you have to use a lot of fancy words to really confuse people. Period doubling, bifurcation, suddenly split. This is the period doubling bifurcation. What happened is that x, y, z in the phase plan, it will go to the other dimension and come back. So the phase plan, instead of just one circle, it becomes two circles. And two circles is not exactly identical. This is x, y, z. If I plot only x, y, it's like this. So it's one notch within the other one. And this is the higher frequency, this is a lower frequency. This is a higher long period, this is a short period. Yeah. So if you give this data to me, what I did is I immediately separate in two components. Yeah. Component number one, component number two. Component number one actually has if you look, it has a wider wave and narrow wave, wider wave and narrow wave. Yeah. And these two IMF, the rest of that are very small. This is 1, this is 5, this is 0.05. Yeah. The reason that we have this is that when you get to period doubling, it's already not strictly not regular. It already start to get into chaos. Yeah. So so the frequency that we got is that we have one basic frequency, another one up and down, up and down, up and down. Look like this. And if you compare this frequency, you'll find that yeah, this up is equivalent to this narrow frequency, this down is a wider frequency. So you have a wide frequency and narrow frequency, wide frequency and narrow frequency. And this, however, is the Fourier type of representation. You have a fundamental frequency, then you have lots of harmonics. Yeah. And superimposed on that, we have, this is our answer. Our answer is here, and with higher frequency and lower frequencies here. Higher frequency and the lower frequencies here. Yeah. And we do not have all these harmonics to try to feed that. And if you plot the marginal spectrum, what you find is this. These are full of harmonics. Yeah. You can keep on going. They are all harmonics. What we have is here. This is one frequency, that's the lower frequency component. The higher frequency component has a higher frequency, lower frequency, higher frequency, lower frequency. Alternatively, it's this compared to the mean frequency. And if we plot this region in the linear, see, we have a lower frequency part, that's the background. The higher frequency has low frequency and high frequency, low frequency and high frequency. What Fourier gives you is this frequency. This frequency is the mean of all that frequency. So what Fourier can do, the Fourier is always give you an average. Average over all the time. So, and if the average does not work, you have harmonics, 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 harmonics. Even in linear, you can see the harmonics. So you keep adding harmonics, which is constant frequency, constant amplitude wave. Eventually, you can add up to this frequency distribution, high and low. What this means is that whether you have a slow oscillation or fast oscillation, Fourier gives you the mean. Now, therefore, in this particular case, we can equally claim that Hilbert gives you two components, Fourier only gives one. Except the Fourier say, oh, I'm not one, I also have harmonics. But the harmonics, remember, it's actually mathematical artifacts. Yeah. Mathematical artifact will come back later when we discuss water waves. Yeah. So this kind of mean frequency, I don't think it's reasonable. Yeah. When we analyze the nonlinear signal, I'm not looking at mean. I'm looking at the variation. I'm looking at the detailed mechanisms. Yeah. This totally miss the mechanism. So now we come to the. So we resolve that. I mean, we have frequency, we have continuous frequency totally different from the Fourier. It's not surprising, it's reasonable. Okay. Negative frequency. Why we get negative frequency? When we talk about the instantaneous frequency, we find a lot of time, if we use Hilbert transformation, we do get a negative frequency. Why? Because signal itself is not sufficient. Yeah, it's only necessary to get IMF monocomponent. If you take any data, you do a Hilbert transformation, you get all kinds of unreasonable frequency. Even if you reduce the data to IMF, it's still not guarantee you get a reasonable frequency. If you use IMF directly, go through Hilbert transformation. The instantaneous frequency lecture that I give pointed out that if you violate Bedrosian theory, if you violate Nato theory, you're not going to get a good instantaneous frequency. Yeah, and that's exactly what this paradox is all about. Now, again, negative frequency, this will give you negative frequency. Just because I shift the sine wave a little bit. Yeah. If I shift the sine wave a little bit, and I will get negative frequency. There's nothing wrong with Fourier, nothing wrong with Hilbert. It's all because that you use Hilbert wrong. So the first thing we have to do is to get rid of this. How to get rid of that? Move the line to the sine wave. Yeah, this frequency, this negative frequency, absolutely has nothing to do with the Gabor construction. It's all because you have 0 and you have a circle outside 0. Anytime you have a loop, that loop does not including the origin, you will have negative frequency. That's number one. And it's always the case. So we have negative frequency. We already know that we have negative frequency. Now, so we get shifting. If we have two frequency, two components, and if we have that, we're going to have negative frequency. Yeah, that is just that simple. Yeah, and these are so simple, such a simple example. Yeah, if you do Hilbert transformation, you get 2 cosine. And how come I get 2 cosine and still get negative? Because you have the two combination. The two combination will give you this loop. Yeah, and and you see, we have all kinds of negative spots that have negative frequency. In this case, even worse. So the data need to be shifted. Now, whenever Hilbert transformation loop away from the origin, we'll have negative frequency. Whenever Hilbert frequency pass through the origin, we'll have singular. So those are actually the problem with the data, that the data has not been cleaned, not been reduced to its proper form. So if we reduce this to proper form, we have 2 components, it's no problem. And you change that, you change this, you change, you have different frequency. So negative frequency of the instantaneous value are most due to riding waves. If you have extrema, in between extrema, you have more, in between zero crossing, you have more extrema, you can expect that you will get negative frequency. Yeah. And IMF is a necessary but not sufficient condition for having non-negative frequency. When we do decomposition, then we find that we get IMF. IMF is single component. Presumably, we should not get negative frequency, but that's not sufficient because the limitation of Bedrosian theory. So there are occasions when abrupt amplitude change in IMF, but no riding wave, can also generate negative frequency. Yeah, this is the limitation of Bedrosian, and we have proposed normalization to take care of that. So if we have normalization, we will not have this. Physically, this abrupt change of amplitude also shows the non-local characteristic of Hilbert transformation. The Hilbert transformation is not exactly local. That's true. So resolution, for that case, we can think of all the different examples that I give in the instantaneous frequency computation. Resolution number 5, the paradox number 5, is that if we compute instantaneous frequency, we should use the local data. But Hilbert transformation is not local. Therefore, why you still call that the local instantaneous frequency? The problem is this. Yes, Hilbert transformation is not local, but it has a 1/t window. When t minus tau equal to 0, it gives you a lot of weight. Okay, so 1/t window in Hilbert transformation. But most problem, but this is pretty narrow window. In fact, the non-local property is fully resolved by quadrature. If we get the IMF, And by IMF, after we normalize it, then what do? Instead of using Hilbert, I use quadrature. Quadrature is exact local, right? Quadrature, I have the function, I compute the quadrature, and after I have the quadrature, I take a derivative of the phase, and that's extremely local. So the HHT, when it's first developed, totally depends upon Hilbert transformation. And after I study it, and I find the Hilbert transformation may have problem because it's linear property of the Hilbert transformation, and it will not fully take care of the nonlinear complicated phase function. So I come up with this quadrature method, and once we get the quadrature method, then we are not limited by this 1/t window anymore. So quadrature, using quadrature method, we can have a time frequency distribution. I still call that the Hilbert spectrum, but you don't have to call the Hilbert spectrum. Yeah, but though the solution is no longer a quote-unquote Hilbert spectrum, but in a large sense, I call the Hilbert spectrum. Just like, for example, I called most of the wavelet spectrum Fourier type spectrum. Yeah, it's based on the same principle, but it's through different computation. So even the paradox number 5, it's not a limitation to us anymore. Yeah. So time frequency analysis, now we start to have some new solutions, a new view. And this new view will fully taking care of the non-stationarity and the non-linearity in the data. Yeah. So now, at the beginning of developing HHT, I encounter a lot of this kind of question. Yeah. Not only from the Wigner-Weil camp. Yeah. Many people, the most commonly asked question is, I have 2 components, you only give me 1. This I cannot accept. Yeah. Now, even that, we have a pretty good satisfactory resolution. So I think with this, the time frequency analysis has really become pretty mature, at least in principle. In implementation detail, we still have problems like, for example, how to compute the quadrature if data density is not high enough, and so on and so forth. We may have those may have those problems. So with this, I think you can all go out and use your method and defend yourself. And this will be the end of this discussion. But here is an extension of the locality. See, for example, we have the sine wave with a jump. And this sine wave with a jump violates Bert-Dresden theory. Yeah, we have discussed that. And the discussion is, see, we have frequency that's already gone negative. Yeah, and not only that, even the frequency is not negative, it's no good, it's junk. Yeah, so by the time you violate some restriction, and the answer will not be good at all. So you use spectrogram, you get this, and use wavelet, you get actually a pretty good answer. So now we have to normalize it. To normalize this, sometimes we may have problem. When we talk about normalization, we did point it out certain problem. Sometimes the normalization scheme will actually change the location of extrema and things like that. In the details, we still may have some problems. Yeah. In this case, like if we have the data, we have the old spline, which is just connect all the maximum. Here, the maximum actually go down and go up, overshoot and come up. Yeah. So the extrema is not very good. What we did, the new spline, is that we start to use some section of straight lines. I don't think that's very good. Actually, this was prepared a long time ago. What I would now suggest, if you encounter this, perhaps locally, you can use you can use the Hermite polynomial. The Hermite polynomial is that the monotonically increasing. Yeah, within this point and that point, I have a monotonically increasing. With this, is all monotonically increasing. Then you can get rid of all the extrema overshooting. Even in this case, we still have overshooting, and that's still not good enough. This is one of the methods that I come up with, but it still has it improved a lot, but it's not strictly still not clean. Even with this non-clean method, when you compare with the available method, you'll find that if we use the step function transformation, Fourier transformation, look like this. Yeah, it's very wide, and Hilbert spectrum give you this red. It's much narrower than that, and the carrier Fourier frequency give you this. Still finite, and the carrier frequency, if you use Hilbert, is only one dot. One frequency, one amplitude. Yeah, the precision is really good, and so you can look the original Hilbert transformation. Yeah, generalized zero crossing and improved normalized Hilbert transformation. Normalized Hilbert transformation is still not good, but it's much better than the Hilbert transformation. So resolution, Hilbert transformation is non-local. It is non-local. Yeah, we have to use empirical AM/FM to separate it. Yeah, so once we separate, once you use empirical and renormalize, then compute the frequency with quadrature, then it's perfect local. Yeah. So, summary. The so-called paradox are really not problems when some misconceptions are clarified. I believe the so-called paradox are those harbored by those people that had their mind fixed on Fourier analysis. Everything you got, you have to compare with Fourier. But we know Fourier has certain shortcomings. Yeah. Even if I compare well with Fourier, does that mean that my answer is reasonable? Given that the original Fourier is already proved to be not unreasonable. So instantaneous frequency has very different meaning than Fourier frequency. It's not the same thing. Instantaneous frequency gives you the frequency variation, and Fourier only gives you the average value. And Fourier not only gives you average value, if the one average value doesn't work, it'll keep adding another average, keep adding another average. Those added quantity is mathematically meaningful, but physically it's not. I always give water wave as an example. Water wave has very sharp crest. Any sharp crest has infinitely many harmonics. But the water wave is dispersive. Shorter wave should propagate slower. But for water wave, for the sharp crest to propagate, all the harmonics have to go at the same speed. How can a short frequency wave go that fast? It's not possible. Do they care? No. Mathematically, it's correct. So at that time, they switched to mathematics. So we have very, very different meaning. IF, instantaneous frequency, for special non-monotonic function is for special monocomponent function only. Yeah, but this monocomponent IMF is necessary but not sufficient. Yeah, Even for MF, there's still a problem associated with Hilbert transformation. We can normalize it. After we normalize it, then we don't have to stick ourselves to Hilbert transformation if the phase function is complicated. So the quadrature is the answer. So this is the whole key to all the problems that people has regard to instantaneous frequency. Yeah. So that's the end of this lecture. And if we recall this whole up until now, I have already introduced you to the decomposition and various ways to decompose. And once you get the decomposition, how to compute the instantaneous frequency. And once you get that instantaneous frequency, you can project it on time frequency space and get a spectrum, which is the Hilbert spectrum, as I called it. Yeah. There are other things that we don't have time to share with our colleagues in Japan, because their semester is kind of short. But I will invite you to visit our website. Our website will post on the future lectures on the website, right? This lecture is recorded, right? And the recording is posted on the website. So, in your leisure, whenever you want to look, you can look at the website and look at the rest of the material that will be covered in here. This, for us here, the semester will have another month to go. Yeah. Another thing I have to alert you is that I just posted a set of MATLAB code on the web. It's already on the web. You can download and use this code. My code is kind of, I have a lot of this code because I don't know how to write code. I always ask people to write for me. And sometimes I forgot, so the code has a lot of redundancy and it's different styles. So I've asked someone to go through all the code and pick up the ones that's essential and put it all together in a pretty uniform format. But this gentleman, when he did that, he put it in, rather than .m code, into .p code. .p code means you can have all the help file, but the program itself is absent. We will try to correct that. In fact, shortly I want to have all the code unified and maybe write out as a manual for people to use. So if you want to use it, you can use it now in the code on the website. So on the website, you can download all kinds of references related to HHT. And if you want to read more, of course you can go to the journal, Advances in Adaptive Data Analysis. In the future, and all this lecture like instantaneous frequency will appear in there. And the two-dimensional will appear there, and the Hilbert spectrum and the marginal spectrum discussion will also be there. So good luck, our friends from Japan. Sayonara.
Thank you.
Bye-bye. I hope you learned something. This is the last lecture you will attend. Do you have any questions? Any questions? I think the long distance teaching can convey certain information to you, but unfortunately it's not as good as face-to-face. I'm looking forward to sometime I may visit you guys, because I cannot even see who you are. If I run across you in the street, I will never know that you have listened to my lectures. Okay, so we'll try to get that situation corrected. I'll make a point to visit you guys in the next year. All right? Thank you very much for attending my lecture.
Thank you.
Yeah, bye-bye.
Bye-bye.
Sayonara.